Advanced Algebra, Chapter 6, Lesson 5, and I wanted to do a few examples where we determine all of the zeros of a polynomial expression. I must be hungry. I'm thinking of cereal. Anyway, there's four kind of steps that we want to go through when we're doing this. We want to first determine a list of possible zeros using the rational roots theorem. We then want to use the remainder theorem to determine which ones from that list are actually zeros of the polynomial. We then want to divide that polynomial using synthetic division by those rational zeros, which will then create a quadratic, which we can then use our methods of solving a quadratic in order to determine the final irrational or imaginary zeros. So those are kind of four steps you want to remember to go through. We'll go ahead and do a few of those, and hopefully you'll find this helpful moving forward. As we look at the first one here, we want to determine the list the possible rational zeros. And you remember, using the rational roots theorem, I take the factors of the constant, 1 and 3, over the factors of the leading coefficient, which is here is 1. So I make my list. So these are the possible rational zeros. We then use the remainder theorem and substitute these values in for x and determine which ones will give us a remainder of 0. Now, I can tell by the answer here that both 1 and -1 will produce rational zeros. So, now we want to take those zeros and actually use synthetic division of this polynomial. So, we're going to use the first 0, 1, and we're going to divide. Now, this is x, whoops, I forgot something already. X to the 4th, I don't have any x cubed. 8x squared minus 0x minus 9. So being sure to put in my placeholders, I then want to use my synthetic division. So in synthetic division, we multiply and add, we multiply and add, we multiply and add, and I get a remainder of 0. So that takes care of the 1. Now I want to synthetically divide by -1. And again, I don't want to go back. I just want to continue going down here, and you'll see why in just a moment. So I multiply and add, I multiply and add, and I multiply and add. So you'll notice then I get a remainder of 0, which I should, so -1 is a 0. Now we want to put the variables back in. You'll notice that we started with x to the 4th, so if I put the variables back in here, this would have been x cubed, but then I divided again, so this is x squared. So I have x squared plus 0x plus 9. And this is why we need to do synthetic division, because now we have a quadratic. And the quadratic, using our knowledge of being able to determine zeros for that, we can then determine the last couple of zeros that this polynomial of 4th degree has. Now, this one does not have a linear term, so I can extract the square root. So I simply set it equal to 0, and I solve. So taking all of this, x is equal to plus or minus the square root of -9. Now, the negative we can not deal with in a rational way, so we use the imaginary, we use the I. So this is actually then I square root of 9, and then the square root of 9 is 3. So I have plus or minus 3i. So you can see that is how I get the final two zeros, is I have to get it down to a quadratic. The only way to get it down to a quadratic is to synthetically divide by the zeros that I figure out, or the zeros that I determine, using the rational roots theorem and then the remainder theorem, and dividing those out. Okay? Not too bad, I hope. Let's take a look at the next one here, number 4. For number 4, we want to begin again using the rational zeros theorems. So I take the factors of the constant, 1, 2, 3, and 6, 1 times 6 and 2 times 3 is 6, over the factors of the leading coefficient, which is 1. So these are my possible rational zeros. So I can only have these as rational zeros. So I then use the remainder theorem, substituting each one of these values into the expression, determining which one will give me a remainder of 0. By doing that, I see that both 1 and negative 1 will give me a remainder of 0, so I know that 1 and negative 1 are roots of this expression. I then need to divide synthetically by these so that I can create the quadratic, which would allow me to determine the last two zeros. So we're going to divide by 1. So I have, again, x to the fourth. I have 0x cubed, negative 7x squared, 0x, and then 6, using all of my placeholders. I bring down the first coefficient, and then I multiply and add. I multiply and add. I multiply and add. Whoops, that's not right. I multiply, let me get this right. And then I multiply and add. Again, I have a remainder of 0, which I should get. I then am going to I'm going to divide by the next 0. So I multiply and add, I multiply and add, I multiply and add. Again, I create, I have a remainder of 0, and when I put the variables back in, this was x to the fourth, so this was x cubed, so this one is going to be x squared plus 0x minus 6. Again, now I have the quadratic, which I can use to determine the final zeros. There's no linear term here, so I can set it equal to 0 and simply extract the square root. So x is going to be plus or minus the square root of 6, which does not simplify, so you can see I have my zeros in this manner. Okay? Do a few more examples. I don't think they get too much more difficult than this in this lesson, but we'll take a look at a couple more. So let's tackle number 5 here. I have a constant of 36, so to use the rational root theorem and to begin, I need to make a list of my factors. So I have 1, 2, 3, 4, 6, and then 9, and then let's see, 12, 18, and 36. Those are the factors of the constant. All of those over the factors of my leading coefficient. So my possible lists include plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Basically all of these numbers, plus or minus 6, etc., etc., all of those over 1, and then all of those numbers over 5. So this is a pretty big list. And in the next lesson, I'll show you how to shorten that list a little bit easier than what we're going to do here. So what I would do here then would be to use my remainder theorem and substitute each one of these values into this expression to find out which one would give me a remainder of 0. So that's going to give me 2 and negative 2 out of this entire list. So 2 and negative 2 are going to be my rational zeros. I'm going to synthetically divide by those so that I can hopefully create a quadratic where I can then determine the remaining zeros. So let's divide by the 2 first. So I have a coefficient of 5x to the fourth, 0x cubed, negative 29x squared, 0x, and 36. And so we'll go ahead and divide by the positive 2. So 2 times 5 is 10, and then I add. And then I multiply, and then I add. And then I multiply, and then I add, and then I multiply, and then I add. So I have a remainder of 0, and that works. I just see something may say that's not 0. I was looking ahead. This should be negative 18. Alright, so now that I get a remainder of 0, I divide by the second 0, which I know I should get a remainder of 0 to begin with. So this is multiply and add, multiply and add, multiply and add. So this was x to the fourth, so the first one takes me down to x cubed, so this would end up then being 5x squared plus 0x minus 9. This final quadratic expression does not have a linear term, so I go ahead and simply solve this by extracting the square roots. So I'm going to copy this up here so I have a little bit more room. So I'm going to extract the square root by moving the 9 to the other side. I'm then going to divide by 5, so 9 over 5. So then I'm going to take x is equal to the square root of, taking the square root of this side. So the square root of 9 is 3. over the square root of 5, and then I rationalize my denominator, so I end up with 3 square root of 5 over 5. This is all plus or minus in each step here. So I have the 2 and the negative 2 that I found by using the rational root and remainder theorem. Then using synthetic division and extracting the square root, I determine the final two zeros. In our final example here, we want to go ahead and determine these zeros. So I see here that I have a constant of 1, so a constant of 3, so my factors are 1 and 3, over the factors of my leading coefficients, 1 and 5. So I have a possibility of plus or minus 1, plus or minus 3, plus or minus 1/5, and plus or minus 1/3 as my potential rational zeros. Using the remainder theorem, we determine that -1 is a 0, so we're going to then use synthetic division to divide by that, which will take me to my quadratic, which will allow me to determine the last two zeros. So we're going to divide by -1. So I have 5x cubed plus 5x squared plus 3x plus 3. I don't need any placeholders, so I'll just do my division. So I'm going to multiply and add. I'm going to multiply and add. I'm going to multiply and add. I have a remainder of 0, which I expect. I then put the variables back in. So this is 5x squared plus 3. And because this one does not have a linear term, I can extract the square root by setting this equal to 0. So 5x squared is equal to -3. So x squared is equal to -3 divided by 5. So I'm going to move this up here. X is going to be equal to plus or minus then the square root of a -3 over the square root of 5. The negative root I can't handle, so I'll handle it by using the I. And then we'll rationalize our denominator. So x is equal to plus or minus I square root of 15 over 5. And you can see that we have the correct answer. To wrap things up then, remember the four kind of steps you want to go through. Rational root theorems to determine the list of possible rational roots. Remainder theorem to determine which ones out of that list are rational zeros. Divide synthetically using those zeros so that you can create your quadratic and then solve your quadratic. Now in this lesson we had extracting the square roots for all of them, but that isn't always going to be the case. Usually in that case where they're not, you're going to need to use the quadratic formula to determine those last couple of zeros because the quadratic will have a middle term or a linear term to it.